שלום לכולם. אני מעוניין לפתוח במספר מחשבות אישיות. אני מודה לכם מראש על סבלנותכם למרות המפגש שלי. זהו כנס ה-OpenStack השני שלי בישראל. והכנס הראשון שהיה במאי השנה השפיע רבות על היחים המקצועיים והאישיים שלי. במהלך החודשים האחרונים היה לי העונג להיות בקשר עם אנשים מאוד אינטליגנטים, תכלס, כנים ופתוחים. אני חייב לציין שעד היום במהלך נסיעותיי בעולם הגעתי לישראל שבה האנשים, אתם, קיבלתם אותי בחום יותר מאשר בכל מקום שביקרתי בו בעולם. ולכן אני רוצה להודות לכם. תודה רבה. And now the really challenging part of my presentation is done and I can relax. So what's the subject of this talk? We'll be talking about geographically distributed OpenStack clouds. So what is that? What makes our cloud geographically distributed? Is it a specific distance between sites in kilometers or miles if you use archaic units? Is it a specific mode of organizing our cloud? Is it a specific goal that we want to achieve with our cloud? I'm going to use this definition. If we're building a distributed OpenStack cloud, then I'm going to define that as an OpenStack cloud or multiple clouds, and I'm going to get to the distinction in a moment, that spans multiple geographical sites with limited bandwidth, network bandwidth that is, and significant network latency between them. Now what do I mean by significant? I mean it sort of in the sense as we commonly use it in statistics, meaning non-negligible, or to put simply, making a difference. And in general, we're talking 1 or 2 orders of magnitude network latency greater than in a LAN. LAN Ethernet latency is typically about 100 microseconds, and between sites we usually get on the order of 1 to 10 milliseconds. That is to say 10 to 100 times greater than what we get in the LAN. So that's the definition that I'm going to be using for a geographically distributed OpenStack cloud for the rest of the talk. Now, why would we want that? Why would we want geographically distributed OpenStack clouds? Well, we might have one of the following motivations. And of course, there might be others. The list is by no means meant to be 100% complete. So one of the motivations that we might have for building a distributed cloud is obviously disaster recovery. And if we're building a distributed cloud for disaster protection or in order to be able to recover from a disaster, that means sort of the classic no-brainer motivation for geographic distribution, which is what if an A380 slams into my data center or a backhoe cuts the fiber to my building, something like that. So being able to recover services in a backup site if the primary site we're typically using happens to be disabled or become unavailable. One possible motivation for building distributed clouds. You might also want to achieve some degree of local affinity. And what that means is you may want to host your services in the same general geographical area as your users. Now, most of the time when people think about that sort of thing, they think about performance. But that's not necessarily the only reason. For example, you might want to employ certain considerations about jurisdiction. You might want to offer compliance with a specific set of laws when your users or a part of your users demand that compliance. So for example, I'm based in Europe, so one of the things that we tend to worry about is there are EU data protection directives or privacy directives that hosting providers must follow, and that may be a reason why you're building a distributed cloud to serve your European users in that case. Or you might want to be in a certain area or out of a certain area because you might be fearing that your users are being spied on by some 3-letter government agencies affiliated with 3-letter countries. I'm not going to name names. You might want to do follow the sun. And follow the sun means you would be able to geographically position the location where your services are running based on time of day, time of year, or any other time-based parameters. And it may be cost-effective, specifically in terms of a price-performance ratio, to host your services in such a way that they are always in closest geographical proximity to the majority of your users. And like I said, there may be other motivations, but those are generally the ones that we see the most. So what do we want in a distributed cloud? What are our general expectations for a distributed cloud infrastructure? Now, what I'm going to say, or what I'm going to paint here next, is sort of an ideal picture. I'm not going to say that OpenStack can do this, all of it at this time. I'm not even saying that any distributed cloud system out there can do it, but it's what we would want in an ideal distributed cloud system, and we're going to get to what OpenStack can and cannot do about this in a moment. So one of the expectations that we have for a distributed cloud would be a certain degree of unified user management. So our users, when we give them a set of authentication credentials, then they should be able to use that set of credentials unmodified across the entire cloud. They shouldn't need to care about which specific geographical location they're talking to. They should be able to use those authentication credentials in the entire system. So that's one thing. Our users generally would expect unified user data as well. Now, this is not stuff that we give to them, like authentication credentials, but stuff that they put in the cloud. So that would be the expectation, that the persistent user data that goes into our cloud is persistent and available no matter where specific services run. So generally the expectation would be, if we are uploading or generating data in a specific geography, then we would want something that has that data available even if our service runs in a different geography. So that it would be another expectation. A third one would be a unified virtual network. So in an ideal world, again, we would be able to provide a unified logical view of the network connections between the sites and between virtual machines that may be distributed across these sites. And the important part would be that this unified logical view would be decoupled from the physical network, which might potentially be very heterogeneous. We would also expect unified orchestration. So that would be the ability to automate, to deploy, and to orchestrate services across the cloud. Generally, anything that we expect from orchestration, we expect to work not just in a specific geography, but in all of them. We would expect to have a unified user interface. That would be helpful. That would enable us to manage, to observe, and to modify our cloud workloads from a single UI. Note this says UI, not GUI. The user interface does not necessarily have to be graphical. If we have command line or scriptable interfaces, as we do in OpenStack, for example, we would expect that those also work the same way, no matter which geography, which part of our cloud we point them at. And that is for user interaction. And then, of course, for program and application interaction, we would also expect our API access to be unified across geographies. So that enables us to interact programmatically with the entire distributed cloud in a simple and streamlined fashion. Okay. So when we look at that, taking into account our general expectations, let's skip to which sort of options does OpenStack provide for segregating clouds, which may be sort of a stepping stone to distributed cloud. Segregating clouds meaning, a subdivision of a cloud along geographies. We basically have 4 options for doing this in OpenStack, plus 1. And I'm going to get to the additional one first. The additional one is just to not care, have completely distributed, completely distinct OpenStack clouds in all of your geographies, not care, and then let your users take care of whatever they need to take care of in terms of distribution, which generally is not really a very compelling proposition, which is why we're going to leave it out for now. Okay, so let's talk about these four. One of these options to logically segregate an OpenStack cloud are Nova availability zones. Nova availability zones are a great way to segregate specific areas in your data center, but they're not really very suitable for geographic distribution of clouds. They don't really take network failures in stride too well. It kind of expects the network not to fail. So unless you're actually a telco and you own your fiber and you have built your redundancy into the fiber, et cetera, then this approach really isn't for you, at least not for distributed clouds. It's great for building availability zones within your data center or on your campus, but not necessarily for the distributed cloud use case. Pretty much the same thing. Oh, by the way, if you're not familiar with availability zones, that means that all of our OpenStack services are shared, including Nova, and only by a grouping of hosts that we call availability zones, we segregate the compute hosts specifically, but they're all managed by the same single Nova. Something very similar applies to host aggregates. Again, all of our services are shared, including Nova, and then rather than segregate hosts into availability zones, we group them into these host aggregates. It's a similar approach to availability zones, but we usually don't use it for availability purposes. Rather, what we do with host aggregates is we tend to use them for the ability to place guests on quote-unquote trusted hardware. So if we have a specific set of hosts that is meant to run a specific set of guests, or a specific type of guest rather, then we can put those hosts in an aggregate, and then we can have our scheduler hints when we fire up a virtual machine to say, okay, run this specific workload on this specific group of hosts. So it really has the same limitations as the availability zone approach when it comes to suitability for the distributed cloud use case, which really is kind of nil, except in the corner case that you're a telco and you own the entire network. Then we have Nova cells. Now, Nova cells are, on the Nova side, superior for distributed computing, distributed clouds, compared to the others. In Nova cells, we have a single Nova API service, and then we have a tree, a hierarchical tree of what we call cells that then map, for example, to specific geographies or to specific data centers or things like that. The caveat with that is that it doesn't really do anything good for the distribution or the geographical spread out of any of the other services because it's Nova specific. So it doesn't do anything about geographic distribution for Glance, the OpenStack image service. It doesn't do anything about geographic distribution for Cinder, OpenStack block storage. So again, maybe not so really well suited for running a globally distributed OpenStack cloud. So that leaves us with the fourth option, which is multiple regions. So in multiple regions, we basically have completely separate OpenStack installations. And those are then unified by a single keystone. So a single OpenStack identity service, which also manages the endpoints of and maintains the service catalog for all the other service endpoints. And here we finally have the ability to globally distribute it, and not just the stuff that Nova manages for us, namely our virtual machines, but also globally distribute Glance and Cinder and Neutron and whatnot. So this is really currently, for most people, this would be the only option that we have for building a globally or geographically distributed OpenStack cloud is the multiple region approach. So easy, right? Well, let's take a look at what the real challenge in all of this is. It basically all boils down to replication. And here's an interesting challenge with that. In OpenStack, most of our services split the data that they manage and the metadata that is associated with them. The metadata usually goes into a relational database. Most people will be using MySQL for this, but any relational database will theoretically do, which makes sense because metadata is generally a set of key value pairs which are really nice to stash into a set of tables in an RDBMS. Whereas the actual data that a specific service manages is, guess what, service specific, so it only makes sense to put it in a service specific store. Whether that's block storage or whether that is stuff to manage a network or whatever, or an image that goes into a service specific store. Okay. Now that we have this split between data and metadata, that means that when we are talking about replication in a globally distributed cloud, we must separately replicate the data and metadata while also keeping them consistent. Consistent in and unto themselves, but also consistent with respect to each other. Now, unfortunately, that is practically impossible. Why is that impossible? Well, it's impossible because of this. You're all familiar with the CAP theorem. It basically says that in a distributed system, we get 2 out of availability, consistency, and partition tolerance. We can build a system that is available and consistent but not partition tolerant. We can build one that is available and partition tolerant but not consistent. And we can build one that is consistent and partition tolerant but not always available. There is no overlap in the middle. So how does that affect our problem? Well, our only really reliable multi-site, multi-master metadata store that we currently have available on a general purpose basis for all of our OpenStack services is MySQL with Galera. And that is a strongly consistent system, also known as a CP system, because in the face of a partition tolerance, in the face of a partition, if it can't guarantee that it serves you consistent data, it will prefer not to serve you any data at all. That is to say, it's going to be unavailable. So it sacrifices availability for consistency and partition tolerance. Now, we have several service-specific stores that are also CP. They're also strongly consistent, meaning they're dropping availability in favor of consistency and partition tolerance. One example of that would be Cinder, OpenStack block storage, with Ceph as its backend store, which is strongly consistent, or GlusterFS replicated volumes, which are also strongly consistent. But that means we would have to synchronize their replication stream with the MySQL database so that they're always consistent versus each other. Well, that's almost impossible. But we have other stores that are eventually consistent. They sacrifice consistency in favor of availability and partition tolerance. And one of those examples is Swift and any service using it. Now, Swift is a very core component of OpenStack. Many people use it in conjunction, for example, with Glance, and many people use it by themselves. But for example, if you have any service that's using Swift, such as Glance, then it is fundamentally impossible to synchronize these data stores with metadata in a CP store across multiple sites. Because if you were able to do that, you would be building a CAP system. And that doesn't happen. So luckily, there's 2 exceptions to this. Not to the CAP theorem, but there are 2 services within OpenStack that do not have this split between data and metadata, or have another capability that makes them not fall into this trap, which is great because now we have something to work with. One of those services is Keystone, because in Keystone we really don't have a split of data and metadata. All of the relevant Keystone data actually lives in a relational database, or can live in a relational database, at least that part that actually we do care about in terms of consistency and replication. So that's great. So we can actually use a replicated Keystone, or a MySQL Galera replicated Keystone in our distributed cloud, which is going to be really helpful. And we have Heat. And Heat grew a very interesting feature right before the Havana release, which is we can run it in standalone mode. It doesn't necessarily have to be part of an OpenStack cloud, but instead we can use it to manage multiple clouds. So we can have a single Heat instance that can then orchestrate multiple OpenStack clouds, which is really wonderful. So this is our formula for geographically distributed OpenStack. MySQL Galera-based Keystone plus per site Keystone regions. So every one of your sites maps to a Keystone region. Regions we've had in Keystone forever. Plus multi-cloud standalone Heat equals geo-distributed OpenStack cloud. That is as well as we can do it right now. That's sort of our current status. So what does this look like? this is, I'm going to walk you through this real quick. So what do we have is here in this picture, we have 4 regions. They are using, they're all running their own Keystone service, but the important part is that the Keystone service uses as a backend a relational database that is multi-master, multi-site synchronized. And then we have a heat instance, which for aesthetic purposes I had to put sort of in the middle of this, otherwise this picture would have looked horrible, which can then orchestrate multiple clouds. By the way, just a side note, it's important to understand that if we want to use Galera replication for Keystone, but no Galera replication for any other database content, then we need separate MySQL installations for the Keystone database and the other services databases, because you may be familiar with MySQL replication. MySQL replication has selective per database replication, so you can actually turn it on and off for individual databases. And even for individual tables, MySQL Galera doesn't have that, so we actually have to have a separate MySQL instance for our Keystone stuff, but that's okay. All of the other services are per region, and everything is unified by this replicated authentication database and a standalone multi-cloud heat. Well, everything else is by itself. We might like or we might not like that. So the question is, can we replicate anything else? Can we make sure that our data is synchronized for any of the other services? Kinda, sorta. And I'm going to go into a few of these examples here. So for example, we actually have the ability to replicate glance data and metadata in a reasonably multi-master, semi-atomic fashion using a little tool called Glance Replicator, which has existed since Folsom. We've had it for a long time. It was written by Michael Still, who was, I think, then at Canonical and is now at Rackspace. It atomically replicates both image data and metadata to a remote glance. There's the issue with it that it's on demand, not streaming, and it's one way, so multi-master replication isn't really part of its design, but it does replicate image UUIDs and thus catches duplicates, and so circular replication really is expected to work here. The thing is, it hasn't gotten a lot, Glance Replicator itself hasn't gotten a lot of love since it was first written, but that's basically a question of using it and trying it out and see where the corner cases are. So we have kind of a story for that as far as our images is concerned, and that will get us relatively far in our distributed cloud because things like our golden master images is something that we would really like to have in multiple locations, such that when we fire up a VM in Singapore, we wouldn't want to populate our Nova image cache from London. It would be much nicer to actually have the image available there. So we kind of have a story for that. What about Cinder? We kind of would want that for Cinder as well. So it would be kind of great if we had something like that for Cinder. Of course, a snapshot, an image is kind of static, whereas a volume is continuously being written to. So for Cinder, we would really kind of want continuous volume replication, like volume mirroring. And if you were at the Hong Kong Summit, or if you are watching the Cinder blueprints, you're going to see that, hey, there's actually a blueprint for volume mirroring. And there was a design summit session for it, and there's actually work on it that it's being done. And it's actually from a team at IBM in Haifa. Anyone from that team here? Yes? Is that you? Awesome. That's Avishai, right? Hello. Good to see you. So it looks like it solves this problem for us, and it might in the future, but not quite. Not yet, at least. So volume mirroring, as is proposed for Icehouse, will deal with replication within a single Cinder instance only, and not replication between Cinders, which is still good, and it's helpful to have, and it's great to plug certain asynchronous replication facilities into it. But for what we want in the distributed cloud use case, it's not helping us just yet. But nonetheless, this may be a very, very important stepping stone toward true distributed cloud volume replication. There's interesting challenges in Neutron. We really don't have much of a replication story for Neutron yet. There are interesting things that you can do with Neutron at this point if you know your way around BGP and dynamic routing. So for example, it is conceivably possible to have an L3 agent in multiple locations that manages IP addresses from the same IP network. And once you do that, once you're capable of doing that, you can then use a notification facility in Neutron that when a specific floating IP is being associated, you can announce that to your router, because your router can also do host routes. And then all of a sudden you would be able to move a specific floating IP from one continent to another, and it would still be available to your users, which would be great. Right now that involves some manual scripting, but it's not entirely undoable. Nova, we really don't have a cross-cloud migration story yet. So there's no such thing as sort of a live migration from one region to another, but then maybe that's actually sort of an unreasonable expectation. You should probably just orchestrate at the heat level, really. So this is how far we can get at this point with Havana. We have multiple keystone instances unified through MySQL replication. A single standalone, potentially multi-cloud heat that can talk to all of these regions, and we have the ability to do some image replication with Glance Replicator. This is what you can do with Havana. With Icehouse, we might see more, but I think this is actually a pretty good start. So one other thing that I want to mention, just as a general rule, basically if you want to unify your cloud, there is no way around orchestration. And you can unify distributed clouds reasonably well today in OpenStack by using proper heat orchestration. And there's very interesting stuff happening in heat in the Icehouse cycle as well, such as potentially being able to describe a multi-region stack, a multi-region array of heat resources that span, like in one template, spanning multiple regions, which is kind of nice. Okay. And that concludes my talk. A few words. If you like this talk, feel free to tweet at hastexo or find us on Google+. Pretty much all of my talks are Creative Commons licensed. This one is no exception. This is all under CC BY SA. The sources are up on GitHub. Feel free to snap this QR code now if you want the GitHub sources. 3, 2, 1, too late. And these are actually the slides that you just saw. So for those of you that want to come back reviewing the talk, you are certainly welcome to do so. With that, I thank you very much for your attention. Do we have time for a couple of questions, or are we out of time? One question. Okay, we have one question. Yes? So, yeah. Nope. Yes and no. So yes, you're absolutely right. One of the things that happened in the Havana cycle was the Swift 190 release, which included global clusters, which is fantastic because it allows us to put data into Swift that is then globally replicated in an eventually consistent system. That is great. But it doesn't resolve the issue of getting your glance metadata, for example, across. So you still have the problem of having metadata in a strongly consistent system and your actual image data in an eventually consistent system, which is impossible to reconcile. But if you're only talking about the object storage specifically, you're absolutely right. That is something very important that, that happened in this release cycle, and it's a very, very helpful addition to Swift. For those of you more interested in Swift, which I just couldn't touch upon in this presentation in much detail, just due to time constraints, there's a very interesting keynote from the OpenStack Summit by Dan Wilson from Concur, talking about what they did with Swift Global Clusters. And then, of course, there's a lot of information to be found on the OpenStack website, on SwiftStack's website. There's a lot of talks out there by John Dickinson that you can probably find on YouTube. And if you're interested in Swift Global Clusters, then I warmly recommend those. So with that, I thank you very much for your time and enjoy the rest of the afternoon.